out how many, what's the propagation delay before the payload is actually being visible at the I/O. These are very straightforward parameters, and the other one is this implicit behavior, the probability on this. So these are very general parameters, not specific at all. It describes a very large, these are very general parameters that all these deterministic hardware Trojans will need to have in one way or the other. So from that perspective, the hardware Trojan characterization is very general. So now if you increment the D, right, so yes, if D is as large as the number of wires, then clearly I can, with incredible complexity, you can figure out all these hardware Trojans. I can detect those. But in practice, the D, the dimension, must be, to reach good complexity, must be, say, at most, say, log n or whatever you want, and that will reach the sub-exponential class. Now, we can design hardware Trojans that can be that. We can do that. So we can go beyond sub-exponential complexity, but those types of hardware Trojans are actually exhibiting some algebraic tricks. But that means that you can use other techniques to figure out how to detect those types of Trojans. So it's a very general and very large class in that aspect. So the question is really, the next question is, can we now figure out how can we beat those parameters to set them very large? What kind of hardware Trojans do we then get? How do we design those? And I've really been breaking my head over it for a while, so we can define, figuring out that one particular hardware Trojan that I just talked to you about, but what other types of tricks could be out there? And now the hardware Trojan designer will have a really hard time to get this going. So that is sort of the partial answer to that first question, because we still have the cat and the mouse game, but it is played in a very different way.
Thank you, Martin. Let's thank you one more time and turn it over to others. So Professor Russell received his PhD from MIT, and he's a professor in computer science and mathematics at the University of Connecticut. His research is quite diverse, going from quantum computing to cryptography. Today, we're closing this last session with a talk on cryptography, clipping the powers of cryptographic attacks. Alex, take it away.
Okay, great. Yeah, that title was specifically designed to confound Laurent. Okay, and so instead of trying to explain what all the mysterious words are in this title, let me just start with a motivational story. So the first part of the story is the great chapter of cryptography. This is cryptography in the ivory tower, and I gotta tell you, from up here, it looks great. Okay, so when we study cryptography in academia, how do we play? So we pretend that cryptographic algorithms are always perfectly, faithfully implemented. We pretend that cryptography runs on perfectly idealized hardware. But we also pretend that we have this clear, crisp division between the parts of the system that are public and dangerous and the parts that are private. And with all of these arrows beside us, we then can confidently model security with abstract security games. So this has been an extremely successful endeavor. On the other hand, where the tire meets the road, when we're forced to actually deploy cryptography in the real world, it turns out to be really messy and complicated. So implementation, deployment are complicated, and then there's the single biggest problem with real deployment, which is that there are humans involved. And today I want to talk about one perspective on the challenge of really deploying cryptography in the real world, and that's the problem that when we deploy cryptography, we typically use cryptography implemented by a third party. And today, this talk, I'm going to focus on what can happen if the third party that implements our cryptography is adversarial. So this area of cryptography is sort of playfully called kleptography. And it turns out that there's philosophically kind of remarkable threat that can emerge here. And the threat is that if we permit a third party to implement our cryptographic algorithms, the threat is that a third party implementation can leak private information, but it can actually do so in a way that adheres perfectly to the specifications of the algorithm. And the word perfectly here really means perfectly, information theoretically perfectly. So if this comes as a surprise to you, that's good. At least I've held your attention for the first 90 seconds of the talk here. So this entire area is, as I said, sort of playfully called kleptography. And at least in the theoretical community, the study dates back to, say, the mid 90s. And let me just give you an example to whet your appetite for what kinds of things are possible here. Let me talk a little bit about RSA key generation. And this example will make sense to you even if you've forgotten the details of how RSA works. So to develop an RSA key, what do? You pick two big primes, you multiply them together. That gives a number that I call capital N on this slide. And you then generate essentially a random number E, and that's the encryption exponent. And then you do some number theoretic voodoo to get this decryption exponent. For that, you need the two primes. So the real salient feature here is that there's some private data that we want to make sure does not leak out. At least that's the factorization of N. And there's also part of this RSA key that's going to be made public, E, that consists essentially of just random bits. Okay, so now let's consider what can happen if let's see here, if the adversary gets to implement the RSA key generation algorithm. So the idea is that the adversary is going to embed in this key generation algorithm a backdoor, let's call it Z. And in fact, calling it a backdoor makes it sound very sensational and romantic. It's just going to be a little bit string that is going to act for the adversary as a key. And so here's what the adversary does. He implements the key generation algorithm so that as things get started, it behaves perfectly faithfully. It generates two big primes, it takes their product, it produces the big number N. But then when it's supposed to produce E, the encryption exponent, which is just supposed to be a bunch of random bits, it actually takes the first half of E, and instead of producing random bits for that half, it actually embeds in that first half of the random bits an encryption of one of the two primes that factors N. And it does that using this backdoor, Z, as an encryption key. So it should be clear then that if this key gets used for anything of interest, the manufacturer, that is the adversary that produced this key generation, this subverted key generation, can easily break the security here because he or she actually has one of the primes, can actually factor N. What's more interesting about this is that if you use a probabilistic encryption of the type that we know how to do, you can actually arrange things so that E, this encryption exponent, looks like perfectly clean randomness to anyone who doesn't have this backdoor that's embedded in the algorithm. Okay, so that's the motivational example. Right, so the takeaway message here is that adversarial implementations can leak information. And, not to put too fine a point on it, but this is obviously particularly destructive when it's applied to primitives that are widely understood and believed to be secure, like RSA. In fact, it's common for people to talk about RSA as though it's been proven secure. And furthermore, if the output of this algorithm is actually statistically clean, so you can't distinguish it from the output of a perfectly faithfully implemented key generation algorithm. So, sort of curiously, this entire area was not given a lot of attention by the cryptography community, even though there were some early papers on it in the 90s. Of course, once we were confronted with the specter of an NSA backdoor in the dual EC pseudorandom generator, things picked up and there was sudden renewed interest in what kind of attacks are available in this situation. And more interestingly, what you can do to immunize yourself against the possibility of subversion and subliminal attacks like this. So there was a really remarkable paper by Bellar et al., and they study what they call algorithm substitution attacks, which, as you can guess from the name, are very like the RSA attack I just described to you. And they do something, in a sense, much more devastating than what I just showed you. They actually observe that if you have any randomized algorithm that has been presented to you by an adversarial implementer, you can use a nice trick called a steganographic channel to leak information over time in a way that is statistically clean. So they proposed a remedy for this. So having identified randomized algorithms as the main culprit, they suggested that we try to implement cryptographic tools using deterministic algorithms only that are indeed easier to test. And then, because there is always one part of a cryptographic system that has to be randomized, that is key generation, they put this in a special category and say, we're going to have to trust that this is done correctly. There's also been some specific attention given to pseudorandom generators trying to model what happened with the dual EC pseudorandom generator. In particular, there are a nice impossibility and possibility results in some interesting models that involve clean randomness. So I'll just move along here. So what's the current status of this area? We know very little. I would say it's just wide open. So we have very few general mechanisms around for immunizing good primitives. We have considered very few cryptographic primitives in this setting. And perhaps even more discouraging is the fact that the crypto community has no clear agreement on what the right models are to even understand these kinds of attacks. So for example, basic questions like, which of our cryptographic algorithms do we permit to be subverted? Do we allow the innocent user who's using these algorithms to have nice, clean randomness? Or do we assume that the adversarial implementation is somehow even aware of the user's private state on the computer? Finally, are the algorithms that have been presented to us that are supposed to do things like key generation, are they allowed to internally maintain state so that they can evolve over time? So all these are important questions that need to be somehow captured in a reasonable algorithm if you want to say something meaningful about it. Yeah.
Has anything like this really happened?
There are lots of authoritative accounts of this in the press. I guess I won't step out on a political gangplank, but yeah, you can read about the dual EC subversion. Okay, great. So what are the long-term goals here? So we'd like to develop some simple defense mechanisms that we can use to ensure against this kind of kleptographic behavior. And we would like to do this even under the assumption that all of the algorithms that are relevant for cryptography can be simultaneously subverted by an adversarial packager or implementer. And of course, we'd like to do this in broad generality, right? We would like to revisit the entirety of cryptography and build a new theory that we sort of playfully call kleptography that gives us some basic satisfactory models that lets us rebuild the entire edifice of cryptography. Okay, so there are a couple of results I'd like to talk about today. The first thing we do is we try to set down a family of various models that let us capture some of these attacks and let us be precise about what it would mean to defend against them. Specifically in those models, we then focus on developing secure one-way permutations and secure one-way trapdoor permutations, and then we use those to build pseudorandom generators and to build secure digital signature schemes. So I'd like to make one mention about this, which is that one of the great successes in cryptography has been to use reductions, typically black box reductions, to take simple primitives and put them together in ingenious ways to produce richer, more powerful cryptographic tools like digital signatures. So one kind of terrifying angle here is that it turns out that even very basic black box reductions that are secure in cryptographic settings can become insecure in the kleptographic setting. And so the reason I say this is a little bit terrifying is that this suggests that we not only need to revisit the security and structure of the basic primitives that we have, but we also need to invent new ways to argue about how to put those primitives together to produce richer cryptographic tools. Okay, so let's go ahead and talk about the models here. So in our model, we invent three entities. There's the adversary, so his evil doings you've already been introduced to, so it's going to be his job to provide us with potentially subverted implementations of well-specified cryptographic algorithms. Then later, once he has delivered those to us, he's going to try to break them. Then there's the innocent user who uses the subverted code, but we're going to add one more entity to the mix here. This is the watchdog. So the watchdog gets a chance to test the potentially subverted algorithms, comparing them with the specification before they actually get put into the innocent user's hands. So here's how the story goes. So it begins with Act 0. This is where a secure specification is designed by friendly cryptographers. And we assume everyone knows how the specification works. We assume that in absence of any kind of subversion, the specification is actually secure. Okay, so then Act 1 is that the adversary gets his hands on the specification, and he actually provides a potentially subverted implementation of this specification. Now, before this actually gets deployed, thankfully we have the watchdog. So what the watchdog does is he's given the adversarial implementation. He, of course, also has the faithful implementation that was produced at time 0 by the cryptographers, and he's now allowed to test these two implementations. Now, when I say test, I really mean black box testing. So he's not allowed to look deep into the soul of the adversary's code. So the testing is all done completely black box. He gives it inputs, he gets outputs from it. So there's no source code review, if you like. So the watchdog is allowed to ask this code questions, get things back, and I'll talk a little bit later about what kinds of things the watchdog can actually guarantee. Okay, so once the watchdog washes his hands, says this looks good, finally we return to the setting of classical cryptography. We play a classical standard security game between the adversary and the innocent user, who of course has to use this potentially subverted code. And depending on the kind of power that we give to our watchdog, we may or may not let the watchdog watch this security game also to ensure that things in the game look okay. Okay, so how do we put all this together into a notion of security? So we say that a primitive is kleptographically secure if for any efficient adversary that gets to provide us with this subverted implementation, there exists a watchdog out there so that either the watchdog finds a discrepancy between the specification and the actual implementation, or this implementation is actually secure according to the classical definition. So this definition here describes what we call as an offline watchdog. That means the watchdog gets the code, he does his checking once and for all, he certifies it, and that's the end of his involvement. You can investigate stronger watchdogs, and in fact we have to do that in order to get some feasibility results. You can investigate watchdogs that are allowed to watch the security game. You can even investigate godlike watchdogs that look carefully every time one of the primitives are called. But I won't talk about those in detail today. So what can the watchdog do? Well, the easiest thing clearly has to be to say something meaningful about a deterministic algorithm. That's got to be the easiest case, right? So the watchdog cannot ensure that a deterministic algorithm behaves correctly on every possible input that could be given to it. But if there are some particular distributions of inputs, I call them public distributions of inputs that are of interest, the watchdog can certainly draw from those distributions over and over again, test this deterministic algorithm, and see that it does the right thing. In this way, the watchdog can guarantee that with very high probability, on specific public distributions of inputs, that deterministic algorithms are behaving the way they ought. Randomized algorithms are trickier, so in this case, the best the watchdog can do is ensure that on, for example, particular inputs, the distribution produced by the potentially subverted implementation is computationally indistinguishable from the distribution produced by the spec. So this, and indeed, randomized algorithms, you know, as introduced by Bellar et al., are really one of the problematic areas in this whole setting. Okay, so let's talk about something specific. Let's talk about one-way permutations. So a one-way permutation is a function that's easy to compute but hard to invert. And you can think about a one-way permutation as the sort of fundamental building block for symmetric encryption. So what's the classical security game for a one-way permutation? Well, we actually typically when we talk about one-way permutations, we talk about a whole family of permutations. So each one has a little name. That's the index, we call it I. And there's some generation algorithm that produces this index. So the classical security game is the innocent user generates an index. That's the name of the one-way permutation that she is going to use today. Then a random value x is chosen. The innocent user applies the one-way permutation that has this name to the value x, hands that off to the adversary, and the idea is that the adversary should not be able to invert the permutation there. So the adversary wins if he can actually produce an inverse here. So to try to close in on this idea of what it would mean to subvert a one-way permutation, oh, am I really so close to the end of my time here? What time do you want me to close up here, Laurent? 2 to 3 minutes. Oh, no problem. I have like 45 slides, so we should be good. Okay. Okay, so what is a forgeable one-way permutation? A forgeable one-way permutation is a permutation that is indeed a perfectly good one-way permutation unless the adversary gets to give you the name generation algorithm. So we have two games that we're going to put in contrast with each other. The first is the classical cryptography game that defines security for a one-way permutation, and this function is going to win that game. Adversary cannot invert. However, if the adversary has the luxury of producing the algorithm that gives you the name of the function that he wants you to use, then the adversary can win this game. So I won't talk about any more details. I will say one nice fact about this. Nice if you're looking for a new area of cryptography to study, not so nice if you're actually in the business of producing good cryptography that you want to deploy in the real world, is that it turns out that forgeable one-way permutations exist if and only if trapdoor one-way permutations exist. And that means that we have a sort of painful fact here, which is that if there is any public key cryptography at all, then we have to live up to the possibility, we have to live with forgeable one-way permutations in the sense that, that I talked about there. Okay, well, so unfortunately you're not going to hear the awesome part of this talk, which is how you actually protect yourself against this. So we develop a simple immunization strategy that essentially involves hashing the name of the function. So that's great. It turns out there are some issues. Oh, this slide you would have loved so much, you won't get to see that. And then there's some natural criticism for this, which is if you're going to hash the name of a one-way permutation, this sort of pretends that all names are equally easy to get a handle on, that it even makes sense to define a hash function on the space of all names of functions. Well, if you think about your favorite one-way permutation, RSA, for example, the name of that function has some algebraic structure. It's not even so obvious that you can define a natural hash function that works on those names. So we fix that problem by working in something called the split program model that asks the manufacturer of the cryptographic code to separate the code into two parts. One part that produces the random bits and the second part that is deterministic. And this lets us get some traction on the issue of controlling the output. Okay, so we also talk about digital signature schemes. We talk about pseudorandom generators. I already bemoaned the fact that black box reductions don't typically survive in the cryptographic setting. So what do? We develop some technology that allows you to protect essentially against one-shot randomized algorithms. That is, I don't want to oversell these results, We don't completely handle the problem of randomized algorithms in a kleptographic setting. All of the settings that we can actually handle using this technology can put up with exactly one call to a randomized algorithm, the one that does key generation. Okay, so there's a huge amount. This area is an undiscovered country. There are all sorts of beautiful things that come next. And yeah, next year at this time, I can tell you what comes next. Okay, great, thanks.
Thanks, Alex. We have time for a quick question. Since we've seen Matrix rebooted, now it seems like it's cryptography rebooted. Any question?
Actually, for one of those, is what we're seeing with like some of the signature collisions that were like in SHA-1 and MD5 are examples of what you're describing up here?
I hope not. It could be. You know, unless you know the details, the inner details of an algorithm and a specification, it's of course hard in general to tell if cryptographic failures in the algorithm are due to malicious intent, or are really due to subversion, or are just due to idiosyncrasies in the algorithm that were unintended by the designers. In the case of those, I would suggest it's the second, but who knows?
Thanks.
Okay, good. So let's thank Alex one more time. And we have our coffee break now.